You are here because you would like to excel in O-level pure chemistry and combined chemistry, chemical bonding by the help of advanced chemistry. I wanted to create an animation for this video, but unfortunately for the sake of 2025 O-levels, I did not have time. My apologies. But anyway, let's get started and stay tuned. So, this part of chemical bonding is with regards to the physical properties, right? There are some parts that earlier that you learned with regards to chemical properties, and by now you should have known that the chemical properties, when it comes of a chemical compound, right, it basically largely depends on which group the cation and the anion lies in. Okay, but now we're going to do to the physical properties. So some examples of physical properties are those that are not involving chemical reactions. So involve things like boiling point, melting point, so likewise for electrical conductivity, density. Well, we don't really cover it here, but solubility, yes, we do. All right, so let's get started. Most examination questions would like to test you on boiling points, right? So actually, the syllabus have 4 types of compounds you need to know. So actually, what I stated was ionic compound, a simple covalent molecule, then of course the metals and the giant covalent structures. However, unfortunately, I realized that there will be no space. Hence, I had to move them over here. I had to move the giant covalent structures to the next page. Okay, so enough for the rule. Let's get started. So this boiling point and melting point, and you are basically going to account for 3 things in your answer. And this is and this acronym you have to follow here. It is SEB. So S stands for the structure, and then E stands for the energy needed to overcome, right? And of course, which forces attraction, and then B is to bonding. So you describe the bonding. So in an ionic compound, this a giant um ionic crystal lattice structure, right? Then okay, then this one I should cancel. Then this one is there's a large amount of energy, right, needed to overcome the strong electrostatic forces of attraction, right? So the keyword here is basically the electrostatic force of attraction. Don't say intermolecular, right? Because ionic compound is not is not a molecule, right? Ionic compound is an ionic crystal lattice. So it is basically the electrostatic force of attraction. And this electrostatic force of attraction, it causes the ionic bond between the oppositely charged ions. In the exam, if you can state which ions are oppositely charged, it's even better still. So for instance, if let's say you're given um a giant ionic lattice of, like, let's say, calcium oxide, right? So it will be between the electrostatic forces of attraction between the Ca2 plus ions and the O2 minus ions, which are oppositely charged. All right. So without further ado, let's move on to simple covalent molecule. So simple covalent molecule, as the word suggests, this is a molecule, right? This compound is a molecule. Okay, so it's a simple molecular structure, and there's a small amount of energy because you are overcoming the weak intermolecular forces of attraction, and this is between the molecules. Another word for intermolecular forces of attraction is van der Waals forces. So please take note of this word, right? The keyword over here is intermolecular, right? No other substitution is acceptable unless you use van der Waals forces. Van der Waals forces is basically a synonym to describe the intermolecular force of attraction between covalent molecules. Okay. I will actually cover a set of misconceptions later, so that you shouldn't write in your answers. Okay, so then with regards to metals, as for metals, again, there's a giant metallic lattice structure, so there is a large amount of energy that is needed to overcome. Again, sorry, I forgot to write one word here. It is the strong electrostatic force of attraction. So remember, electrostatic force of attraction is always strong. Okay, then this is between the positively charged metal cation and the sea of delocalized electrons, right? So Okay, then so the keywords here is a strong electrostatic force of attraction, right? All this over there. Then of course between this positively charged and of course where is this state of delocalized electron is actually in between. It's actually in between the metal cations, right? The positively charged metal cations. Okay, now let's move on to electrical conductivity. So some questions like will ask you to explain the electrical conductivity of ionic compound. Please do note you have to account for both in the you have to both account for both the aqueous and molten state and as well as the inability to conduct in the solid state. So these are the keywords here, right? Um so what I wanted to mention here is that now in the ionic compound, right, the only thing that is responsible for the conduction of electricity due to or rather as a mobile charge carrier is only the mobile ion. There is no free moving electron in the ionic compound, right, to act as a mobile charge carrier because the thing is in the solid state the ions the ions are held in fixed positions inside a crystalline lattice structure. But when it's dissolved in water, right, dissolved in water, it's going to sort of dissociate fully, right, to form ions. So this crystal lattice structure is going to break down. So that is when the ions become mobile. Okay. Then this one over here for the simple covalent molecule, because as the word molecule suggests, there are no ions, so there's no electron, you don't see any free moving electrons. So do these molecules carry any charge, like any net charge? No, not really, right? So because of this, there's no charge carrier. They cannot conduct any electricity, right? Then this one, right? Um, this one is the one thing is responsible for the conduction of electricity is the sea of delocalized electrons, right? Because these electrons, as the word delocalized suggests, they are free to move, right? You can treat it as like a homeless person, right? Don't you agree that a homeless person is free to move around the streets? So same thing for a delocalized electron. It's like homeless, right? It doesn't belong to any metal cation, right? So you can just like move around in between the mechanical ions, hence they act as a mobile charge carrier to conduct electricity. Likewise, another misconception is that many people think that because the positive in metal charge metal ion carries a charge, so it can also conduct electricity. But this is not true because the metal ion is actually held in a fixed position. Only the delocalized electrons are the ones that are free to move around. It's like it's sort of like um it's sort of like relatable to what you call your ionic compound. The ionic crystalline lattice structure, especially in solid state, true, the ions do carry charge, but when they're held in fixed positions, they're not free to move around. So it's not charge carrier is not just sufficient. You need a mobile charge carrier, right? One other misconception that I wanted to clarify here is that RMFOA is not the same as covalent bond, because covalent bond is actually an intramolecular bond, and when you say it's an intramolecular bond, means it's within the molecule. In IMFOA is actually intermolecular. That means it's between molecules. So for those of you who don't understand what I'm talking about, I'm going to show you here in the diagram. Okay, so the diagram I wanted to show you was actually this. Okay, so this is actually an intracovalent bond between atoms, and this is strong. So this is basically right. This covalent bond, right? As you can see here, right? If you learn what is a covalent bond, you'll notice that there are actually some sharing of electrons going in over here. Okay. Then this one. There's also an intermolecular force of attraction. This is an intermolecular force of attraction, or what you call the van der Waals forces. So basically, there are no shared electrons inside here, right? So it is basically as you can see, right? Um, this is one molecule. This is one molecule, right? This is another molecule, right? So this is one. This is one molecule. This is another molecule, right? So this is intermolecular force of attraction. So as you can see, this is within the molecule. so this covalent bond, right? Okay, people, for your extra understanding, I'm going to write down there that covalent bond is formed by the sharing of electrons. And this actually wants you to, okay, actually this one means to do, this wants me to sidetrack a bit, and this one means to bring it here. So these are three levels of understanding for matter for or ionic bonds and covalent bonds, right? Based on difficulty. So on the basic level 1, ionic bond is a bond between a metal and a non-metal, and a covalent bond is a metal between a non-metal and a non-metal, right? Then level 2, you need to know what's actually happening, right, during the bonding. So level 2 is the intermediate level, where the metal lose electrons and the non-metal non-metal gains electrons, right? Then for the non-metals wise, they are going to share the electrons in the covalent bond, right? Then of course level 3, right, this is the most difficult level. So there is actually an ultimate transfer of electrons from a metal to a non-metal in an ionic bond, right? So that is how you show in your dot and cross diagram, right? Um, how they transfer, so they're going to split according to the ratio, right? So let's say CaCl2, right? So CaCl2, there are two Cl minus, right? So Ca2 plus, Ca to form Ca2 plus is going to lose two of its valence electrons, right? So these two valence electrons is ultimately going to transfer to the two Cl minus atoms. So they're going to split equally. So each Cl atom will only receive one valence electron that is originally lost by by calcium when forming Ca2 plus. Then for covalent bonds, it is basically the sharing of two bonding electrons, right? So one bond, as you can see, right, one bond in the Lewis structure, like all this, right? Lewis structure is super common in organic chemistry, right? Your C, then you get a bond, then a H, right? So each bond represents two bonding electrons, right? And each of them, for two bonding electrons, each bonding electron is contributed by each of the atoms. So as you can see, this is a hydrogen molecule, right? This hydrogen contributes this dotted electron. This hydrogen contributes this cross electron. So overall, this is a single bond, but there are two shared electrons, right? So this actually for you to understand what is going on. So this is actually a chemical property. This is a chemical property, but this is a physical property, because this is the one that's responsible for boiling point and the melting point, right? Okay, then then let's move on to solubility, right? So in solubility, this one is soluble in water, and so the ionic compound is soluble in water, and I actually did a connection because I told you that Chem paper 2 is about um joining your the knowledge, right, is to other chapters. So I actually did a connection. So soluble in water, it is the same as aqueous state. As aqueous state suggests, it contains of water, H plus OH minus. Okay, so when it's soluble in water, it's going to dissociate or ionize fully to give your mobile R ions, because these are ionic compounds, right? So this is actually a recall from acid base and salt chapter. Okay, so this one is soluble in water. Then it is insoluble in an organic solvent, because organic solvent is actually a covalent. It's actually mostly made of covalent molecules, right? So it's very hard to dissolve an ionic molecule in a covalent molecule. Okay, then this one, in the for the covalent molecules, it is insoluble in water except for hydrogen halides. So hydrogen halides, when they dissolve in water, so I give you a very famous example, HCl. By now, you O-level students, you have recognized that HCl is actually an acid, right, when dissolved in water. So if you don't know what I'm talking about, so in aqueous stage, right, so let's say hydrogen halide, hydrogen halide, chloride, right, HCl, if you don't notice, when it's not, okay, so HCl, it does not behave as an acid unless it is dissolved in water. So when HCl is not dissolved in water, it is essentially called hydrogen chloride, right? The chloride is the chloride anion. It's actually a halide anion, so it's considered part of a hydrogen halide. So when you dissolve in water, the HCl is going to dissociate or ionize fully to give H plus and the halide anion. So in this case, I'm talking about Cl minus. And then if you connect, you see this is a recognizable ion. So if you connect your knowledge to acid base answers, so you notice that this is the presence of H plus causes hydrogen halide when dissolved in water to display acidic behavior. All right. Then of course it's also then of course the covalent molecules are usually soluble in organic solvents because organic solvents are also covalent. Metals, they exist usually as solids, so they are insoluble in water and organic solvents. Let's move on to the giant molecular structures. Okay, so now silicon dioxide, right? Silicon dioxide. Okay, so again, so as you can see, these two they are tetrahedral in shape, but this one is basically have hexagon. It's basically like hexagonal, many layers of hexagonal rings. Okay, so this one giant covalent tetrahedral structure, right? Then the bonding is one silicon atom forms covalent bonds with four O atoms, but one O forms covalent bonds with two Cl atoms, right? So basically, I'll explain this later, right, using the help of a diagram. Okay, then this one, so because of this, right, large amount of energy is needed to overcome strong covalent bonds, right? Because of this is basically macromolecules. So when I say there's a giant covalent molecular structure, that means there are over millions of atoms. So basically, there are over millions of atoms for me to not even consider the intermolecular forces of attraction, right? So that is the reason why I'm actually considering, because the quantity is so big, there are millions of items. So it is within means for me to go and control to talk about the or rather talk about the intermolecular concentration. So for that's why I talk about the strong covalent bonds, right? So in this case, for giant molecular structures, when you're breaking we are accounting for bonding and melting points, and going to account for the large amount of energy needed to overcome the strong covalent bonds. And now let's be specific, so between the silicon and the O atoms. Now, diamond is again an electrode of carbon, but now it's in tetrahedral arrangement. So again, tetrahedral structure. So it says more straightforward. Tetrahedral structure. So almost four covalent bond. It's also one covalent bond with four other carbon atoms. So large amount of energy is needed to overcome strong covalent bonds between the carbon atoms. Right? Then this one, graphite. So graphite is actually made up of many hexagonal layers of carbon atoms. So if let's say you people don't know what I'm talking about first, right? Let me show you with the help of a diagram. So I'm going to show you with the help of a diagram over here. Okay, so right. Okay, so just now this was ionic compounds. So this is basically how the ionic lattice looks like. So as you can see, they are basically so there's actually the bonding between the green, purple, green, purple. They're alternating, right? So that is actually the bonding between the oppositely charged ions. Then in the metallic lattice, right? As you can see, the Na plus ions here are held in fixed positions. Only these small little guys here, like the E minus are the ones that are free to move, right? And these are the ones that act as the mobile charge carriers. And then where's the strong electrostatic force of attraction? The electrostatic force of attraction is between the positively charged metal cation ion and the decolized electron. So this is actually the electrostatic forces of attraction, right? So as you can see, unlike charges, as you have learned, unlike charges attract, so that's why causing the electrostatic force of attraction. Then for this was silicon, right? So for silicon, honestly, right? So let me draw an arrow. Okay, so this one, oops, I need eraser. Okay, so this one is actually representing okay, so this one is actually representing an oxygen atom, right? And then this one is actually representing a silicon atom, right? So ultimately, if you all was to notice, the ratio of the silicon atom to the alcohol atom as is one is to the ratio of silicon atom of the oxygen is 1:2. Hence the formula SiO2. Okay, then this is diamond, very simple, right? So basically this is a carbon atom, 1, 2, 3, 4. So there you go. Okay. Then how about graphite? So graphite, I actually want to talk about it. Okay, so let me pause my share. Right, let me stop the share. Okay, so graphite. This is actually what's going on in graphite. So basically, so each layer is called graphene. Each layer of hexagonal ring is called graphene. Then many layers of graphene is going to form graphite. So it's then between the layers, they're actually weak. They're actually weak intermolecular force alterations. Yeah. So this one is intermolecular because it's between the layers, right? So it's also the same as van der Waals forces, right? So this one giant covalent structure. So but this one there's only three others covalent bonds with three other C atoms because the last one is not used. The last valence electron is not used for bonding, right? So in the hexagonal arrangement in every graphene layer, so again large amount of energy needed to overcome strong covalent bonds between C atoms. This one very straightforward. Okay, so this one right, this one for regards to electrical conductivity, it is a no. So it's basically an electrical insulator because it is a because it is tetrahedral bonded, right? So all the valence electrons are used in bonding. So when it's all the valence electrons are used in bonding, right? There are no delocalized electrons left, right? So same thing here, same for diamond, tetrahedral. But then for graphite, right? For graphite, out of four covalent electrons of carbon, only three is used for covalent bonding. So there is one lone electron that is left. And this one electron is basically delocalized, right? So that is why it is free to act as a mobile charge carrier, right? And move along the hexagonal layers. Okay, so this one over here, so please take note of it, right? So you must specifically go and write that it is the fourth valence electron that is delocalized. It is not all electrons because three electrons are used in bonding. But by right, remember I told you in the earlier session that carbon can already form. Okay, carbon can share four valence electrons to form four covalent bonds, right? So that's what I meant. The fourth valence electrons by right should be form a covalent bond, but now it is delocalized because there's no covalent bond to form with, right? So okay, hardness, right? So this one is SiO2 is very hard because you know its uses, right? But diamond, you have to know some of its uses. So it's used for cutting, drilling, and jewelry because men know for its hard properties. Hard properties because it's tetrahedral, right? Tetrahedral, and of course strong covalent bonds, right? And it's tetrahedral. So for sure, um, this is unlike graphite, right? So for graphite, this is very strong and slippery because now these are actually layers, right? And these layers are actually held by weak van der Waals forces or intermolecular forces of attraction, right? So they are weak, right? So the layers can actually slide over past each other easily. So the fact that you say that the layers are able to slide over each other easily, right, is actually a keyword that you must have present in your answer, right? Yeah, of course the other keyword is this thing over here between the hexagonal layers, right? So because of this, it can be used as a lubricant. And now, I also want to draw your attention to the use of graphite as an electrode. So if you remember your electrolysis chapter, so graphite is an inert electron. Why is it inert? Because it's an allotrope of carbon, right? It's an allotrope of carbon. But yet, it is able to conduct electricity. Why? Simply because of the fourth delocalized electron. So that is why graphite can be used as an electrode, right? Due to its ability to conduct electricity. Okay, so without further ado, these are basically some diagrams showing how the graphite layers looks like. All right. So if not, I hope that this session has managed to benefit you, and I will see you back for acid, base, and salts. Thank you for your attention, and have a pleasant learning experience by Airbus Chemistry.